Hi everybody, this is our group presentation for Deep Learning for Computer Graphics. We are presenting Deep Q Learning for Atari Breakout. My name is Eric Ho.
My name is Jacob Roberge.
And I'm Kasra Yasdani.
And let's get started with this presentation. So our task was to create an AI that's able to play Atari Breakout on an emulator using Deep Q Learning. Our first goal was to complete a game of Breakout. Our second goal was to minimize the time it takes to complete a game of Breakout. And our stretch goal was to use the same model to play other games on the Atari 2600, just like they do in the DeepMind paper. And just a quick overview of what our presentation is going to be about. First, we will go over what is Deep Q Learning, and then why we chose Atari Breakout, then how we actually applied Deep Q Learning to our project, the challenges and problems we faced, and then finally, our results and takeaways. So first, let's define Deep Q Learning. Deep Q Learning combines the concepts from reinforcement learning and deep neural networks. To decide what action an agent should take in the environment, Deep Q Learning will first sample a state from the environment. In our project, the state is an RGB image of the game at a given frame. The current reward of a state and the expected reward from taking an action are combined in a weighted algorithm to create a Q value of each action. The action with the highest Q value will be the one taken at that step in the game, and this process repeats for the entire game. As you can see from the picture, we have an environment here. We observe the state, pass the state through the network, calculate the reward, and based off that reward, take an action in the environment, and this process repeats. So to optimize the neural network, we first have to store an experience replay that will contain states, rewards, actions, and Q values from the environment. This experience replay is vital for training, but cannot hold all past data since it will take up too much memory. And we will use two identical neural networks in architecture, but with different weights. One to predict the Q values, and another to predict the target Q value, i.e. labeling the data. The experience replay is sampled to create a batch of data to train on. This batch is then passed through the Q network and the target network, and their outputs are compared to compute loss. The Q network is trained with back propagation every time loss is computed, and after a predetermined number of steps in the environment, the weights from the Q network are copied over to the target network. Now, what's the difference between normal Q learning and Deep Q learning? The main difference is the method in which Q values are calculated for every state action pair. So in normal Deep Q learning, a Q value table for every state action pair is maintained, so it maps each state action pair to a Q value. Whereas in Deep Q learning, we estimate Q values with a neural network. So normal Q learning can handle small and discrete environments better, whereas Deep Q learning can handle continuous actions and states. And in environments with infinite state action pairs, it's not feasible to maintain a Q value table. So that's where Deep Q learning solves this problem.
All right, thank you very much, Eric, for setting this up. Now I'm going to talk about our motivation for choosing this project, and specifically the Atari Breakout game. A lot of us have been playing Atari Breakout ever since we were a kid. This game actually came out in 1976, and it is a very popular Atari game. Steve Jobs and Steve Wozniak were the first ones who started making this game. So in this game, there's a layer of brick lines on the top third of the screen, and the goal is to destroy them all by repeatedly bouncing a ball off of a paddle that we are, as a player, we can control. This game is a rather simple game. There is not very much complications to it, and the action space is therefore not super huge. And we thought it is a very interesting project to apply what we've learned in this class. So I am going to focus on the Markov decision process that Eric said we had set up for the Q learning right now. And I'm going to focus on the state of the system. But before so, I would like to go over the libraries that we're going to use to simulate the game. We are going to use the OpenAI Gym library, which provides a lot of environments for actually simulating different games. Atari games are a huge part of the libraries. It also can help you simulate games such as chess and etc. The Atari game Breakout is actually in there, so it gives us a really nice interface where we can focus on the Q learning algorithm rather than actually implementing the game and making the software backend of that. So we are going to incorporate the Atari game from the OpenAI Gym library for our work. So now I'm going to talk more about the similar work that has been done in the literature. It turns out that actually we've not the first ones who have attempted this. Other people have been interested in this problem for quite a while now. One company that has really focused on reinforcement learning recently has been the DeepMind, which I think they are a part of Google. And they have actually implemented the Q learning algorithm in the year 2015 to play the Atari game. And they implemented the Q learning algorithm. We are going to be all different from them in our implementation, and we are going to detail this in a few slides. Other works that have been done in our area is one work by Jacob Chapman and Matthias Lechner that they used the approach that the DeepMind paper used to only play the Atari Breakout game. And in their implementation, they actually used TensorFlow as the backend of their implementation. And they ran their algorithm for about 10 million frames to be able to beat or win in the game of Atari Breakout. So now I'm going to focus a little more on the state part of our Markov decision process. So because of the focus of this course that is on computer graphics, we are using only images of the game being played as our input to the Q learning algorithm. So we are getting raw images from the game actually being played, and we are going to process those rather than actually specifically giving the position of the ball and the bricks to the algorithm. So the images of the game that are being played are 160 by 210 by 3. They are RGB image inputs, and we're going to pre-process them to grayscale and cropped version of them, and then we are going to reduce the size of the image almost by half, 70 by 85, for training purposes.
Pre-processing simulating motion. If we have a ball that is if we just take a still image of a ball in motion, we can't know if it's going up, down, left, or right. That was a previous problem we were having when we were training the reinforcement learning agent. So we fixed this by stacking the 4 images together in a 4 by 70 by 85. Apparently, DeepMind also did this, which we found by later reading on it. And then we put that 4 by 70 by 85 image into the model, and the convolutional layers actually extracts the relative position of all the balls and is able to find out the velocity of the ball. On the left side, we could see the original image, and on the right side, we could see the processed image. We cropped the left and right side, top and bottom, and we converted it to grayscale, and we also used downsampling to reduce the image size by half. Our PyTorch implementation, we made a convolutional neural network with 3 convolutional layers and a single linear layer at the end. The first convolutional layer extracts the features from the 4 channels of the images that we input into the model, and our final linear layer maps all the features that were extracted from the 3 previous convolutional layers and maps it to the 4 action spaces that an Atari game takes. hyperparameters. Our gamma value is a hyperparameter that's used to discount the next q value. This is important in the Bellman equation. Our epsilon is the chance of our policy taking a random action. Our batch size is just batch size used for learning. We will be sampling from our replay memory a batch size and then learning off that. Our learning rate is learning rate of the model. Our games added to replay buffer. We will be adding X amount of games to the replay buffer every epoch. Then we will be extracting X amount of batches and then training those batches per epoch as well. Finally, we will be updating our target network, our target queue network, every X amount of intervals. Action step. We will be first resetting our state. Then while episodes are not finished or while the game is still not done, we will be either taking a random action based on epsilon, or we will be taking the maximum index from the queue network. Then we will be stepping through based on the action, and we will be saving the next state reward. And then we will be concatenating the 4 previous states into a single image with 4 channels. And then we will be saving that data in experience replay. For our learning step,
mic
we will
feedback
be
off.
taking
Mic off.
in n iterations. So we will be iterating over n batches. If our counter is below a certain threshold or above a certain threshold, we will be updating the target model's weights with the model's weights. Then we will be extracting a batch size worth of episodes from the replay history. Then we will be setting the Q values to the predicted values from the model, and we'll be taking the target Q values from the predicted values from the target model. Then for each slice from a mini batch, we will be taking the Bellman equation. We will be using the Bellman equation on those. If it's done, it's just going to be the reward. Else, it's going to be the max argument of the next, or the max of the next state from the target Q values. And then we will be we'll be multiplying it by the gamma of that max and adding the reward. Then we could just take the loss of the Q values and then the acted Q, and we will be performing back propagation on that. For our next step in our agenda, we will be talking about our challenges and problems. GPU programming. For GPU, it's very important to minimize the amount of data transfers from the host memory to the GPU memory. To do that, we actually save the entire replay memory onto the GPU. This is different from the DeepMind paper, where they saved all of it on the host memory and then just transferred it to the GPU memory every time they wanted to train off that batch. This means that our replay buffer is markedly smaller than the DeepMind paper. We thought that would be okay since we were updating the replay buffer quite often. And then the game is emulated on the CPU, so we wanted to just quickly generate each game's worth of data and then train off the replay memory, which is already on the GPU. This means that we were able to get a GPU utilization rate of 90%, which is much better than we had before. The network is trained on the GPU, and then we store all the observations on the GPU. Action space size. Originally, we had 18 potential actions on Atari. As you can see at the bottom, we had multiple unnecessary redundant actions that could be done. This means that the Q network had to learn a much larger action space. This was inefficient because there was pretty much only 4 valid actions in Breakout. So we could either leave the action space as is. Finally, we thought it would be best or more optimal to reduce that action space to only 4 values, and then this increased the training speed by order of magnitude.
So now we're going to talk about another challenge in training the Q-learning algorithm, which is the problem that exists because the data points are not IID. So the data points that we are feeding into the Q-learning algorithm are coming from just straight up coming from the Breakout Atari game. Therefore, there is a high amount of correlation between each frame of the images that are being fed into the algorithm. This high correlation between the data points means that we are violating the basic assumption of the IID data points in the system. Therefore, the gradient descent algorithm is not going to converge as the theoretical results promise. To alleviate this problem, we are going to randomly sample from each episode of the algorithm being played so that we are generating some artificial randomness in our input images so that we are able to accelerate the training so that we can converge faster.
And now we'll talk about our results and the takeaways from this project. So we do have success in able to train a model that's able to play a game of Breakout. The network is able to learn the control systems for Atari and play the game like a human. While we were not able to successfully complete a game of Breakout, we believe with more training time that this network can beat a game, and due to the aggressive frame skip of our emulator, our model was not able to converge. So alongside of more training time and a lower frame skip, that our network can beat the game. Some key takeaways. Deep Q learning is simple in theory. You have an environment, you take a state, calculate a Q value, and then use that Q value to compute loss and train a model to learn the game. It sounds simple enough, but in practice, implementation took a lot longer than we expected. We ran into many errors with PyTorch, with formatting the data, GPU memory running out in general. Overall, we trained the final model for over 10 hours, and the model was still not efficient as possible. With more training time, we believe this model can effectively beat a game of Breakout. And here are just some references that we used for this slideshow. Thank you very much. That is our presentation.